Have you ever wondered how a single flap of a butterfly's wings in Brazil could set off a tornado in Texas? Welcome to the hidden mathematical matrix that governs our seemingly random universe, chaos theory. Today, we are peeling back the layers of unpredictable systems to reveal the rigid mathematical laws hidden underneath. We will explore how simple equations can generate infinitely complex behaviors, uncover the historic breakthroughs of pioneering minds, and walk through concrete numerical calculations that prove chaos is not random, but perfectly deterministic. Whether you are a mathematics student, an engineering professional, or a curious mind, this deep dive will completely transform how you view reality. Let us dive straight into the beautiful, structured world of mathematical chaos. To understand chaos, we must first contrast it with classic linear and predictable dynamics. In classical Newtonian physics, systems are often linear or neatly solvable. A linear system satisfies the principles of superposition and homogeneity. Mathematically, if an input x produces an output f of x, then doubling the input to 2 times x results in exactly twice the output, written as 2 times f of x. In these traditional systems, small changes in initial conditions lead to small, proportional changes in final outcomes. If you launch a projectile with a tiny variation in its initial angle, its landing point shifts by a similarly minuscule, predictable margin. For centuries, science operated under this paradigm, assuming that if we could measure the present with perfect accuracy, we could predict the future with absolute certainty. However, the vast majority of our natural world does not conform to these clean, linear abstractions. Nature is profoundly nonlinear. In a nonlinear system, the output is not directly proportional to the input. The governing equations contain terms where variables are multiplied by themselves, raised to higher powers, or cross-multiplied with other variables. This nonlinearity introduces feedback loops where the output of one state becomes the amplified input for the next. As a consequence, small variations do not remain small, they grow exponentially over time, completely shattering predictability. The formal discovery of mathematical chaos traces back to the late 19th century with the brilliant French mathematician Henri Poincaré. In the late 1880s, King Oscar II of Sweden established a prestigious mathematical prize to solve the infamous three-body problem. The problem asks for an exact mathematical solution tracking the gravitational movements of 3 celestial bodies in space, like the Earth, Moon, and Sun, governed by Newton's laws of motion. While the two-body problem had been solved perfectly by calculus, the three-body problem proved resilient. Poincaré attacked the problem using new geometric techniques. During his research, he made a shocking discovery. He found that certain orbital trajectories were so incredibly complex and intricately tangled that it was impossible to write down a closed-form analytical solution. Poincaré realized that even if the equations governing gravity were entirely deterministic and free from randomness, a microscopic error in pinpointing the initial positions of the planets would grow so rapidly that long-term predictions became utterly meaningless. He wrote that a tenth of a degree variance in initial conditions could produce a completely different cosmic arrangement later on. This was the first formal mathematical realization of deterministic chaos, though the tools of his era were not yet advanced enough to fully visualize it. The true dawn of modern chaos theory arrived in 1961 with an American meteorologist and mathematician named Edward Lorenz at the Massachusetts Institute of Technology. Lorenz was attempting to model weather patterns using an early digital computer, the Royal McBee LGP-30. His model used a system of 12 nonlinear differential equations to simulate atmospheric convection currents. One day, wanting to examine a specific sequence of data for a longer duration, he decided to rerun a calculation. To save time, instead of restarting the entire simulation from the very beginning, he typed in the initial values directly from a previous printout. He entered the value 0.506, which was rounded to 3 decimal places, whereas the computer's internal memory held the highly precise 6-decimal figure of 0.506127. Lorenz left his office to grab a cup of coffee while the computer crunched the numbers. When he returned, he was astonished by what he saw. The new weather simulation started out identical to the previous run, but within a simulated period of just a few weeks, the two lines began to diverge dramatically, eventually forming two entirely different, unrelated weather patterns. A microscopic discrepancy of less than 1 part in 10,000 had completely altered the global weather forecast. This monumental realization led Lorentz to coin the term butterfly effect, formerly known as sensitive dependence on initial conditions. Let us analyze the mathematical definition of sensitive dependence on initial conditions, or SDIC. Consider a dynamical system defined by a map or a continuous function. Suppose we have two starting points in our state space, denoted as x sub 0 and y sub 0, which are separated by an incredibly small initial distance delta x sub 0. If the system exhibits chaotic dynamics, this tiny initial distance separates at an exponential rate over time. Mathematically, the distance at time t, written as delta x of t, can be approximated by the expression delta x sub 0 times e to the power of lambda times t. In this formula, the Greek letter lambda represents the Lyapunov exponent. If lambda is negative, the trajectories converge, meaning the system is stable and predictable. But if lambda is positive, the distance between the two trajectories blows up exponentially fast. This positive Lyapunov exponent is the definitive mathematical signature of chaos. It means that no matter how advanced our computers become, or how many decimal places of precision we use, any measurement error, even at the quantum scale, will eventually expand to dominate the entire system, making long-term forecasting fundamentally impossible. To see chaos in action without complex differential equations, we look to a deceptively simple mathematical model called the logistic map. Popularized by the biologist Robert May in 1976, it was originally designed to model how animal populations grow and collapse in environments with limited resources. The equation is written as a recursive difference equation x sub n plus 1 equals a times x sub n times in parentheses 1 minus x sub n. In this equation, x sub n represents the current population ratio as a value between 0 and 1, where 0 means total extinction and 1 represents the maximum theoretical capacity of the environment. The index n represents the generation or time step, so x sub n plus 1 is the population ratio of the next generation. The variable a is the growth parameter, a constant that dictates how rapidly the population multiplies. The parameter a must be chosen between 0 and 4 to ensure the population stays within the boundaries of 0 and 1. Despite its simplicity, as we vary the value of a, this single formula transitions from perfect stability to absolute chaos, serving as a pristine laboratory for studying nonlinear dynamics. As we systematically increase the growth parameter a in the logistic map, the behavior of the system undergoes a series of dramatic mathematical transformations known as bifurcations. When a is between 1 and 3, the population stabilizes completely at a single, unchanging value called a stable fixed point. No matter what the initial population x sub 0 is, it always gravitates to this steady state. However, the moment a crosses the threshold of 3, this fixed point becomes unstable, and the system splits into a period 2 cycle. The population begins to oscillate back and forth between two distinct values from year to year. As a increases further to approximately 3.449, another bifurcation occurs, and the system splits again into a period 4 cycle, alternating between 4 unique values. This rapid splitting is called the period doubling cascade, doubling to period 8, period 16, and so on. This cascade accelerates at a precise geometric rate governed by a universal constant discovered by Mitchell-Feigenbaum, which equals approximately 4.669. Finally, when a reaches approximately 3.57, the period becomes infinite, and the system plunges into absolute chaos, where the values never repeat. If you are finding this breakdown valuable, please take a brief second to like this video and subscribe to the channel for more deep mathematical insights. To fully grasp this mathematical phenomenon, let us perform a concrete, step-by-step numerical calculation using two distinct values for the growth parameter a. For our initial condition, we will set the starting population ratio x sub 0 to exactly 0.60. For our first example, let the growth parameter a equal 2.50, which represents a stable regime. To find the next generation x sub 1, we substitute these values into our equation. X sub 1 equals 2.50 times 0.60 times in parentheses 1 minus 0.60. First, we calculate the term inside the parentheses. 1 minus 0.60 equals 0.40. Next, we multiply 0.60 by 0.40, which equals 0.24. Finally, we multiply 2.50 by 0.24, which gives us an exact value of 0.60 for x sub 1. Notice that x sub 1 is identical to our starting point x sub 0. If we calculate x sub 2, we get 2.50 times 0.60 times 0.40, which again equals 0.60. The system has reached a perfect, stable fixed point at 0.60. Now, let us contrast this with our second example, where we push the system into the chaotic regime by setting the growth parameter a equal to 3.90, while keeping our initial condition x sub 0 at 0.60. Let us compute the first few generations step by step. For the first generation x sub 1, the formula gives x sub 1 equals 3.90 times 0.60 times in parentheses 1 minus 0.60. As before, 1 minus 0.60 equals 0.40, and 0.60 times 0.40 equals 0.24. Now, we multiply 3.90 by 0.24, which yields x sub 1 equals 0.9360. Let us proceed to the second generation x sub 2 using this new value. The calculation is x sub 2 equals 3.90 times 0.9360 times in parentheses 1 minus 0.9360. The term inside the parentheses is 1 minus 0.9360, which equals 0.0640. Multiplying 0.9360 by 0.0640 gives approximately 0.59904. Multiplying this by our growth parameter 3.90 results in x sub 2 equaling 0.23362. Let us do one more iteration to find x sub 3. The formula is x sub 3 equals 3.90 times 0.23362 times 0.76638. Multiplying 0.23362 by 0.76638 gives 0.17904. Finally, multiplying by 3.90 gives x sub 3 equals 0.69826. Look at this sequence of values, 0.60, then 0.9360, then 0.23362, and then 0.69826. The numbers skip around violently with absolutely no apparent pattern, demonstrating how a simple, deterministic formula produces chaotic randomness. To visualize these multidimensional chaotic behaviors, mathematicians use a conceptual tool called phase space. Phase space is a geometric space where all possible states of a dynamic system are represented, with each coordinate representing a specific state variable. For instance, in a simple pendulum, the phase space axis would represent its angular position and its velocity. As time moves forward, the changing state of the system traces out a path or trajectory through this space. If a system is stable and returns to rest, its trajectory spirals inward toward a single point, known as a point attractor. If it settles into a steady oscillation, it loops indefinitely around a closed curve, called a limit cycle attractor. But when Edward Lorenz plotted the trajectories of his chaotic weather equations in three-dimensional phase space, he discovered an entirely new geometric entity, a strange attractor. The trajectories did not settle into a single point, nor did they repeat a closed loop. Instead, they looped infinitely around two distinct wings without ever intersecting themselves or crossing their own paths. This beautiful, complex geometry resembles the wings of a butterfly, appropriately mirroring the nickname of the phenomenon it represents, the Lorenz attractor. The geometry of a strange attractor is not just complex, it is a fractal. Fractals are geometric structures that exhibit infinite detail and self-similarity across all scales of magnification. If you zoom in closely on any small subsection of the Lorenz attractor, you will discover that it contains miniature, perfect replicas of the entire global structure, repeated infinitely. This reveals the ultimate paradox of chaos theory. A system can be locally unpredictable and highly sensitive to initial inputs, yet globally bounded and beautifully structured within a geometric attractor. Chaos is not the total absence of order, it is a higher, more sophisticated form of deterministic order. It teaches us that while we can never predict the exact long-term future of the weather, our ecosystems, or financial markets, we can map out the universal geometric boundaries that govern their behavior. This concludes our rigorous journey through the mathematical foundations of chaos theory, showing how order and disorder are two sides of the exact same coin. If you enjoyed this deep mathematical exploration and found it helpful, please like this video and subscribe to the channel right now to help share this knowledge with others.